Welcome, everyone. Welcome to structured and unstructured data pipelines and GitHub star fraud. Today, we're going to be talking a little bit about how we can apply different types of data pipelines in order to figure out who's trying to basically build up fake credibility on the internet. Briefly, a little bit about me. My name is Andrew Moreland. I'm one of the co-founders at Chalk. We are a real-time data platform for inference. What that means is we focus a lot on getting the right data to machine learning models for production use cases really, really fast and potentially with zero staleness. Before I worked on Chalk, I worked on a bunch of machine learning systems at Airbnb, Palantir, a company that I started called Haven, and Credit Karma. Today, we're going to talk about some of the use cases for these types of data pipelines, i.e. why doesn't batch and streaming work in all cases? We're going to talk a little bit about how Chalk solves the problems that are inherent in building real-time machine learning pipelines. And we're going to walk through kind of a focusing example of detecting star fraud on GitHub, inspired by some recent articles from Dagster and a CMU study. So first, let's talk a little bit about why we care about real-time in machine learning applications. I think the historic paradigm for machine learning has been things like batch recommendation or streaming systems. But oftentimes, we need data freshness that's even more fresh than what you can get from those types of systems. So in applications like fraud detection or e-commerce Rexis, on-demand logistics like ride time prediction for something like an Uber or Waymo for being modern, or in all these modern, or in this new wave of kind of AI-powered applications, we need really fresh data so that the interface can react to user actions in real time, rather than if you're typing in a GitHub document or in a Google document. You don't want the autocomplete suggestions to be informed by yesterday's data. You want it to be aware of the context in the document right now. And one of the things that kind of all these have in common is the need for really crisp freshness. If you're doing fraud detection for like a financial use case, you can't rely on pure batch, because if someone's swiping an ATM card at like 10 different ATMs, you really want to take that into account when you're making your predictions. Today, we're going to kind of adjust this fraud focus that we often have with our customers and orient it more towards something that developers are probably familiar with, which is GitHub. There isn't necessarily a strict freshness requirement here, but the subject matter probably makes a bit more sense. So we're going to focus on how we can detect star fraud. And we're going to do that by using data pipelines that we define at Chalk. The high-level concept of Chalk is we let you define feature definitions, data ingestion, and transformations using vanilla Python. And then we use a fairly sophisticated query planner that we've built to translate that idiomatic Python into query plans. We run those query plans in an engine called velox, which is an analytical query engine that Facebook put out to power their internal use cases. They use it to power this thing called Prestissimo, which is kind of like a C++ accelerated version of the open source project Presto. They might quibble with whether it's an open source project or not. Famously, just kind of two forks of that. And one of the really interesting things about Chalk is we let you integrate arbitrary Python user-defined functions, things like large language models, arbitrary pandas code, NumPy, into those feature derivation pipelines. And we execute all these things in true real time. Sometimes folks say real time means streaming. For us, we're happy to reach out to APIs or transactional data sources like Postgres in the middle of computing features to deliver to your model. And here's kind of a bird's eye view of what those data pipelines look like. Basically, this is a screenshot from the web application that we ship along with our query engine. And we've kind of broken out, it's rendering roughly a DAG of the kinds of computations that might be included in something like the demo we're going to walk through today. In the bottom left, you can see that we're pulling in data from, like, in this case, a Postgres source using a libpq-based driver. We're flowing some of that data through calls out to external LLM providers. I think in this case, we're going to talk about Cerebras. We're running basically optimized aggregations over some of that data, combining that through a Python library, NumPy in this case, and then finally returning the ultimate result. And there's lots of interesting support for declarative caching, validation, things like that. But I think it'll make more sense once we start to walk through what this actually looks like. first, I want to talk a little bit about the problem that we're going to be addressing today. Some folks may have seen the articles that have come out recently about GitHub star fraud. I think everyone's probably intuitively aware of the problem, but basically, star fraud is a growing issue on GitHub. There's a bunch of motivations for this. You might ask, why are people trying to collect fake internet karma points? Maybe in order of severity. People are interested in it to get hired. They're trying to raise money, and kind of subtly, they're also trying to inject themselves into your dependency graph. So a CMU study found that a suspected 4.5 million fake stars when they did a census of recent repositories on GitHub, and they found a 2 order of magnitude increase in the rate of these fake star incidents in repositories which have been starred at least 50 times in the past couple months. So this is a rapidly increasing problem. And to kind of talk about those 3 motivations, obviously when folks are trying to get hired, we often include GitHub projects on our resume. If you have a lot of stars, probably the hiring manager thinks you're cooler and maybe pays you more money or is more likely to give you a job. The same dynamic applies to venture-backed startups. Basically, capital allocators, venture capitalists don't really know what's going on in the world. They want a nice, simple number to sum up how cool a company is. And stars on an open source project that company manages have become kind of a de facto proxy for company success. So anytime you have a metric like that, people start to game it. And people are effectively paying to inflate their star counts so that they can raise better funding rounds. But the most kind of malicious, maybe the most sinister motivation for star fraud, I think, is that when you are trying to determine what projects to incorporate in your own project, you probably look at a couple of options for any given thing you're trying to solve. And a really quick first cut ranking algorithm is just to sort by star count and pick the one that has the most stars. The problem with this is that really you're basically taking on a huge risk when you incorporate a project. People are really focused on supply chain attacks because if you npm install some random package off GitHub, in a sense, you've kind of given that package root on your production servers. So the malware or the hacking networks have figured this out, and they're getting fairly sophisticated about trying to make fake projects, which maybe actually even function as intended for a while, inflate their star counts so that people think they're cool, install them, and then later on they swap them out with malware. And then this has led to a couple of notable compromises. I think that Coinbase got whacked by this a little while ago. There was another crypto exchange which lost hundreds of millions of dollars to this. Basically the issue is that the networks that are doing this are getting increasingly sophisticated and more able to evade simple detection heuristics. So we're going to use Chalk today to try to build a pipeline which can detect this kind of fraud on GitHub. So first off, we're going to define basically a couple of data integrations. So in Chalk, as I mentioned before, the definitions of data pipelines are just idiomatic Python. So basically, we write simple functions in Python which declare their data dependencies and produce outputs. The way that Chalk infers data dependencies is by looking at types. So taking a step back for a moment, the first step in defining a pipeline in Chalk is basically defining the schema of the data we want to operate on. In this case, we're defining a feature class called the GitHub repo. So basically, we want to model all the data we want to integrate as a simple, effectively data classes or pydantic class. We declare the types. We can maybe specify some information about declarative caching. And then from there, we can start to derive more complicated heuristics. So in the case of like a GitHub user, we can reach out directly to the GitHub API in order to fetch data about this person. Again, since we're using idiomatic Python, we can pull in PyPy dependencies like the GitHub API client and use it to directly map data into these feature classes. Once we've pulled the data into our feature classes, we can start to compute derived features. So we're still working in structured land right now. We're kind of reproducing some of the heuristics that the Dagster paper used to find maybe some competitors of theirs that were paying for stars on GitHub. But basically, we're just pulling in data about basically people's profiles, the stuff they filled out on their website, and trying to figure out whether that person represents a real user. And we can, once we've defined these things, we can go ahead and query for the data. In this case, I'm going to query for a user called Nani Rules 153. If you look at their GitHub profile, you'll see pretty clearly that it's maybe not a real account. And we've mapped in some of the data from this user, and I think even just looking at the data sans the GitHub interface, you can kind of tell that. So you'll note that like their GitHub username is Nani Rules 153. Their Twitter username is Erlianierlean. They have a couple followers on GitHub. They're in Texas. They have no gists. They have a couple repos, things like that. It turns out that this account is actually part of a massive network of other accounts, which all look basically like this. And when we run their data through these heuristics, we get a fraud score in this case of like 0.28. And you can imagine this is on a 0 to 1 scale. So fairly low. And that's because they've actually filled in most of the fields in their GitHub profile. The stuff they filled it in with is kind of nonsense. It's just auto-generated. But because we have actually any data here at all, these simple heuristics, which are checking for things like score with socials, like do they have a user bio? Like is the len of their user bio non-zero? These simple heuristics get defeated by this fraudulent user, and we get a fairly low score. In particular, if we compare this to actually a real user, I'm not to pick on Trenor1, but we're going to pick on Trenor1 today. This real user has a higher fraud score, and that's because they're a real person. They don't have time to fill in every field in their GitHub bio, so these heuristics flag them as risky because they don't have anything. They have not specified a company, and maybe they've not specified a location. I mean, like really, who would? So this kind of highlights an interesting problem in fraud, which is that anytime you make up simple heuristics, the problem is an adversarial problem. The people who you're trying to detect will react to your heuristics, and they will basically adapt to them and then adjust their behavior so that they bypass them. And this is why things like real-time matter. If you have like a 1-day batch delay in your fraud detection pipeline, people will figure that out, and they'll make sure they do all of their attacking within a 23-hour window. So in this case, we can make things a bit more sophisticated. Basically, we can map in more data about these users. So I'm going to go ahead and adjust the data I'm querying for. I'm changing the query name, which specifies a particular set of outputs. So now we're going to integrate GitHub archive data. This is another data source. We've cached a bunch of event data from GitHub on a Postgres instance. And by pulling in more behavioral data about the activities of this user, we're able to basically derive a more sophisticated score for this user. And hopefully, if we look at Nani Rules 153 versus Trevor, we see that the legitimate user has a much lower score than the illegitimate user now. So we're moving in the right direction. And we can even take a look at what these queries kind of look like. Let me pull up the query plan really fast. Navigate to this URL. So here's an example of what one of these query plans looks like. And basically, that archive data is being pulled in from Postgres. We're flowing it through some accelerated Python functions. We're combining it with some expressions which have been defined, and ultimately producing a vector after running it through some standard Python resolvers. I want to talk briefly about what this accelerated Python node means. In these pipelines, because they need to execute on the fly in reaction to user requests, we spend a lot of time thinking about how to make that really fast. So while you see on the screen here things like getp for socials, which are written in Python, it turns out that if you try to run that Python function at 1,000 QPS, you will probably run into latency issues because things like the global interpreter lock and just the general slowness of the Python VM. So what we do is at query plan time, so once that server boot basically, we inspect the AST of your Python functions, and then we transpile it into VLOX expressions, which execute in the Facebook C++ SIMD engine. So in practice, this means that these functions can be automatically converted into GIL-free execution. And because they are running in the VLOX engine, they also scale up really nicely for huge backfills. And when we need to actually compute a training set based on these functions, rather than just doing online inference. And here's an example of like what this translation looks like. You can see that we've basically parsed out this symbolic tree and then converted it into kind of a simple intermediate representation with these VLOX functions. So that a brief aside there about accelerated Python. I think that stuff's really cool. Anyways, the problem with even these even these medium heuristics, which do improve the performance though, is that they can still be gamed. We live, unfortunately, in the future, and it's getting increasingly easy to generate really realistic-looking language and really realistic-looking text or code. So these attacking networks have taken to using basically things like Aider or Claude Code to automatically generate realistic-looking GitHub commits en masse. So it's not just, you can't just say like, oh, is there a bio, or oh, is the length of the bio good, or have they only forked repositories? Now you have to actually basically do code review and look at the contents of the text that they're actually putting on the internet. So the nice thing about Chalk is that we can integrate, in this case, some LLM execution into these pipelines with very little code change. Basically, I have passed the bio of the profile to an LLM and asked it to tell me, is this legitimate social data for this particular user? And this is an interesting fusion of structured and unstructured data. Basically, this is the prompt we're using in this case, and it's effectively a Jinja template where we can include other data about, or include other structured data in the context for the model. And this combination of like free-form LLM prompt plus really structured data about the thing that we're looking at ends up working really nicely as kind of a stage in this structured unstructured pipeline. I think some folks have been calling these like cascade models. Basically, the LLMs are slow and expensive. So we use structured information to basically do threshold-based cutoffs before we actually transition to the LLMs. But the overall combination of the two things is way more effective than either on its own. And in particular, this stands in really nicely for a human. Traditionally, in these fraud systems, you use the models to kind of dump data into review queues, where people take a look at the potentially fraudy events. Basically, people are really good at looking at a GitHub profile and saying, that looks wrong. It has bad vibes. And it turns out that so are LLMs. Basically, if you need to have like a vibes heuristic in your fraud pipeline, you can do that now, whereas you could not really do that 6 years ago. So anyways, we can look briefly at the query plan for this and see that, in fact, it is running a little bit slower now, but also we are integrating some of these LLMs into the pipeline. I can't exactly find them in here, but they're running. So anyways, all this to say, when we're working with our customers on these types of fraud systems, they have a bunch of challenges. Basically, they need to iterate really fast in order to stay ahead of the people who are trying to adapt to their heuristics and attack them. They need to integrate data from all sorts of different systems like Postgres, vector databases, internal APIs, external APIs. They need to perform calculations on top of those data sources. And they need to be able to do things like run large analytical type workloads on top of their online serving code in order to generate training sets. And we've spent a lot of time trying to make all those things work together in a nice homogeneous system where you don't really have to think about the different types of modality. And you might ask, like, again, to kind of restate, like, as AI becomes more distributed and people have access to these things, it becomes increasingly impossible to rely on just structured traditional machine learning to fight these actors. Basically, if you're trying to fight an AI which is trying to abuse you, you kind of need an AI yourself in order to detect the machine-generated attacks. And we're seeing people even move to like agentic workflows where they're using effectively AI agents in order to generate structured heuristics and then run them en masse in order to figure out if they're effective. So they have something which is reviewing basically false positives or false negatives and then proposing new rules for their structured rules engines. And then they're evaluating them automatically in order to figure out if those rules improve the performance of the overall system. So this is just part of a broad ecosystem for us. We care a lot about kind of building these data pipelines, but we also care about monitoring them, making sure they're working effectively, running them in a bunch of different contexts, not just online, and making sure that the data that's coming out of them is correct. Anyways, thank you for basically watching this presentation. I'd love to answer any questions people have about this, about chalk, structured, unstructured, about fraud. I'm here for the next few minutes. We might just be wrapping up. Anyways, thank you all for coming. I enjoyed presenting this, and if anyone has any follow-up questions, you can always reach me at andy@chalk.ai. Thank you.